So next, I'm going to go into some reactions involving aldehydes and ketones. So first, I'm going to go over nucleophilic addition to carbonyls. So like I said before, the carbonyl is polarized because there's a partial positive charge on the carbon and a partial negative charge on the oxygen due to the difference in electronegativity. So nucleophilic addition is when a covalent bond is formed on the carbonyl carbon when a nucleophile attacks and breaks the double bond that it has with the oxygen. So what happens is the oxygen accepts electrons donated by the nucleophile, and then this causes the formation of a tetrahedral intermediate. But the carbon won't reform because there are no good leaving groups attached to the carbonyl carbon. So what happens is the oxygen will accept a proton from the solvent, and this forms a hydroxyl group. So this is the mechanism for the reaction. So as you can see here, this blue nucleophile, it'll attack the carbonyl carbon due to the partial positive charge. This causes the electrons from the double bond to move on to the oxygen, and this causes a negative charge on the oxygen. And since aldehydes and ketones, they don't have any good leaving groups attached to it, it won't be able to reform the carbonyl by kicking off one of the substituents. So what happens in aldehydes and ketones, the anionic oxygen will accept a proton from the solvent, and this forms an hydroxyl group. So this is the final product in a nucleophilic addition to the carbonyl in aldehydes and ketones. Next, so hydration of aldehydes and ketones. This is similar to when I went over protecting groups for alcohols. So what happens is an aldehyde or a ketone will react with water to form geminal diols. So this is when there's two oxygen groups attached to the same carbon. So what happens is the nucleophilic oxygen in water will attack the electrophilic carbonyl carbon, and this will form a tetrahedral product as well. So as you can see on the bottom, the carbonyl oxygen will accept a proton from the solvent, and then the water attacks the carbonyl carbon, and that resonates the electron from the double bond onto the oxygen, and this takes away the positive charge. And in order to form a neutral product, the solvent will take back that proton, but from the other oxygen that was just added onto the carbonyl carbon, and this forms a hydrated aldehyde or ketone. That's the hydration mechanism for aldehydes and ketones. Next, I'm going to go into acetals and ketals. So acetals are formed when aldehydes are reacted to two equivalents of an alcohol or a diol, so a molecule with two hydroxyl groups attached to it. So this forms a primary alcohol with two alcohol OR groups attached, and also a hydrogen as well to the central carbonyl the carbon that was in the carbonyl. When only one equivalent of an alcohol is added, it forms a hemiacetal. So aldehydes, when reacted with one equivalent of an alcohol, it forms a hemiacetal. So only one oxygen is bonded. But when it's reacted with two equivalents of an alcohol or a diol, it will form an acetal. And similarly, ketals, this is when a ketone is reacted with two equivalents of an alcohol or a diol. this forms a secondary alcohol with two OR groups attached to it. So alcohol groups attached. And when only one equivalent of an alcohol is added, a hemiketal is formed. So hemiacetal and hemiketal, this is when only one equivalent of an alcohol is added. So like I said before, this is used for protecting groups for carbonyls. So this could prevent the aldehydes from being oxidized or reduced, and prevents the ketals from being reduced. And you can revert back to a carbonyl, so deprotect it by using aqueous acid in order to convert the acetal, hemiacetal, or ketal or hemiketal back into an aldehyde or a ketone. So this is just the mechanism or the reaction. So when one alcohol group is used, a ketone forms a hemiketal, and then when another alcohol group is used, it forms a ketal. Same thing for aldehydes. Aldehyde with one equivalent of an alcohol forms a hemiacetal, and when another is used, an acetal is formed. And it can be one step if a diol is used. So instead of a molecule with only one hydroxyl group added attached to it, a molecule with two hydroxyl groups, so a diol would complete this reaction in one step. Next, oxidation and reduction of aldehydes and ketones. So like I said, you can form an aldehyde from a primary alcohol using PCC, but when you oxidize an aldehyde with any oxidizing agent stronger than PCC, then you can form a carboxylic acid. So anything like potassium dichromate, sodium dichromate, or the Jones reagent, it will form a carboxylic acid when reacted with an aldehyde. But ketones, they're as oxidized as secondary carbons can get. So no matter how strong the oxidizing agent is, you can't oxidize the ketone further. But when you react ketones and aldehydes with a reducing agent, like hydride reagents, like lithium aluminum hydride or sodium borium hydride, you could form the alcohols that oxidizing agents would form aldehydes or ketones. So when you use the reducing agents on an aldehyde, it would form a primary alcohol again. And then when you use the hydride reagents on a ketone, it would form a secondary alcohol. So on the bottom, as you can see, this is the reduction of an aldehyde back into primary alcohol. If no one has any questions, I'll get around this problem. The reaction between 1 mole of acetone and 1 mole of propanol and aqueous acid will result in the formation of what product? So most people chose choice B, but the actual answer is choice A. So acetone, if you remember, I said ketones, they end in ONE, so ON, and then aldehydes, they end in al, so AL. So acetone is a ketone. So when you react ketone with propanol, an alcohol, this results in a hemiketal. So that answer is hemiketal. If it said 1 mole of acetone and 2 moles of propanol, then the answer would be a ketal. But since it's only 1-to-1, so there's only one equivalent of an alcohol, it would only form a ketal. So there would only be one alcohol added to the ketone group.